In this video, we will discuss the intermediate value theorem and learn how to use this theorem to approximate real zeros of a polynomial function. First, let's define the intermediate value theorem. Let a and b be real numbers such that a is less than b, and let f of x be a polynomial function. If f of a and f of b have opposite signs, then there is at least one real zero between a and b. We use the intermediate value theorem to approximate real zeros within an interval of a polynomial function. Let's see how we can apply this theorem. Consider the function f of x equals x to the fourth minus x cubed minus 2. If we are to use the intermediate value theorem to approximate the real zero for this polynomial function, then we first need to find two consecutive integer values for x that have corresponding function values with opposite signs. Choosing 1 and 2 for x will yield corresponding function values that have opposite signs. We know this because if we substitute the value 1 for x in the function, we get f of 1 equals 1 to the fourth minus 1 cubed minus 2, which equals negative 2. Similarly, if we substitute the value 2 for x in the function, we get f of 2 equals 2 to the fourth minus 2 cubed minus 2, which equals 6. Let's now use the bisection method, which helps us divide the given interval of x's between 1 and 2 to subintervals until we find an interval that best approximates the real zero of the polynomial function. To do this, consider the formula c equals the quantity a plus b divided by 2, where a and b are the real numbers that represent both ends of the interval. Evaluating this formula gives us 1 plus 2 over 2. This gives us a c value of 3/2 or 1.5, which means that we should now evaluate the polynomial function when x is 1.5. By evaluating the function when x is 1.5, we get f of 1.5 equals 1.5 to the fourth minus 1.5 cubed minus 2, which is equal to negative 0.3125. This function value is now significantly closer to 0, and recall that our goal is to find a value of x such that f of x is 0. Comparing the values of f at the endpoints and the midpoint, we'll select the subinterval that corresponds to opposite signs of f. This subinterval is the interval from 1.5 to 2, since these have opposite function values. We'll apply the bisection method again, using this as our interval. So we have c equals the quantity 1.5 plus 2 divided by 2, which equals 3.5 over 2, or 1.75. And so, we can now evaluate the polynomial function when x is 1.75. This gives us f of 1.75 equals 1.75 to the fourth minus 1.75 cubed minus 2, which is approximately 2.0195. Using the bisection method again, this time with the values 1.5 and 1.75, gives us an x value of 1.625. When we evaluate the polynomial function at this value, we get f of 1.625 equals 1.625 to the fourth minus 1.625 cubed minus 2, which is approximately 0.6819. Notice that this number is significantly closer to 0 than 2.0195. This same process can be repeated to receive even more precise x values, leading to positive or negative function values, which continue to get closer and closer to 0. We can approximate that the real zero of the polynomial function is somewhere between the x values of 1.5 and 1.625.